Let us now consider the energy in a sound wave, or other waves for that matter. And I'm just going to give you the result here, because we don't have time for a lot of awesome, but I guess at this point unnecessary detail. Okay? Well, it turns out that the energy contained in the wave is 1/2 Ka squared. Now, those are constants and a physical quantity that you're familiar with. A is simply the amplitude of the wave. The 1/2 K is kind of like that spring constant that we've learned about with springs in the past. So you take a spring and you stretch it. So this constant is based on the nature of the medium itself. Like when we do the springs and we send pulses or waves, traveling waves down a spring, the stiffness of the spring has to do with this constant, like Hooke's constant. And so a stiffer spring has greater energy for a given amplitude, and that makes sense. So a heavy medium would be a bigger K. All right. So that's the energy, 1/2 Ka squared, which is kind of nice because it follows the same form as many other forms of energy, like, the energy of a spring, 1/2 Kx squared. Oh, very similar to that. 1/2 mv squared for kinetic energy. But anyways, there it is. And what are the implications or the direct conclusions from that? The energy transported by a wave is proportional to the square of the amplitude. That's the key point here. So looking at the proportionality, E is proportional to A squared. Now the energy can be described as, what is energy related to? You know the answer to that, I'll bet. It is work. In other words, they're joules. So the unit is the Newton meter. The Newton meter is also a joule. So that's the energy transported by the wave. Okay. Now the term power is the rate at which that work is done. So that's the rate at which the energy is delivered. So it's work over time. And that's joules per second. Unit for that is, that's right, it's the watt. It is the watt. Now we introduced the term intensity. And intensity is defined as follows. If you're not swimming in the definitions here, but so far everything should be review for most of you watching this. And intensity now is simply defined as follows. It's power over area. So more intense means there's a great amount of energy in a given region, or a greater amount of rate of energy, really, specifically, because that's what power is. So it's the rate of energy per time over area. So it's the energy transported across an area in a given time. Kind of like if you're looking at the sun. Well, it's very intense. What does that mean? That the power, or the energy of the photons per time, per second, say, for a given area through which those photons travel, like through your pupil, because that's what ends up getting to your retina, that's really high. There's a lot of energy per second in that little area of the pupil. So intensity is really useful. It's kind of like where the rubber meets the road, so to speak. It brings some ideas together that's kind of like a functional description, say, of how bright something is in terms of how we perceive it. Okay. And the last little mathematical statement here is that the energy is proportional to area. I mean area squared. Okay, so the energy is proportional area squared. And so now we know that here's intensity. It's energy, which is proportional area squared. So intensity would be proportional area squared from this. And divide that by time. Does that change anything? Doesn't change the proportionality. You divide all that by area, and that keeps the proportionality the same. So intensity likewise is proportional to amplitude squared. Did I call this area a second ago? If I did, I apologize. This is amplitude, as we know. Okay, so energy proportional amplitude squared, intensity proportional amplitude squared. Well, let's consider intensity a little bit more carefully. What happens to the intensity of a sound as the distance from the source changes, increases in particular? So we're going to consider a sound source in three-dimensional space. So we're going to get to the real world here, so to speak, and not limit it to one dimension or two dimensions. We're in 3 dimensions now. Even though I'm showing this two-dimensionally, this spherical wavefront of the crest of the sound wave, which is equivalent to like the compression region, the maximum compression region of the sound wave. Well, this thing is spreading out. The spherical wavefront is moving outward, and then when it doubles in size, we have a bubble, a sphere, that's got twice the radius. What's the surface area of a sphere? It's proportional to the square of the radius. So the surface area doesn't just double. It goes up by 4 pi r squared, so it goes up by r squared. All right. Now this sound source, whatever's making the sound, say a siren or a horn or whatever, it's got a given amount of energy that it emits in a given amount of time, so this a given amount of power. So the rate at which it's delivering energy is a constant intrinsically. All right, the actual energy per time radiated by the source. Is that clear? And then, also that energy is radiated outward at a constant rate because of the medium. It's moving at a constant velocity. So it's expanding in 3D. The wave doubles in distance. The energy is then dispersed over how much area? If we go from R1 to 2R1, how much more surface area across which is that spherical wavefront manifested? Is that complicated? How much more area does it have? Hopefully you said 4 times. And therefore the intensity is the same amount of power spread out over 4 times the area. So the intensity does what? Goes down. By a factor of, don't say a half or by a factor of 2, but by a factor of 4. Yeah. All right. Conclusion. I is equal to power over 4 pi r squared. So this is just taking it a little more to a higher degree of specificity. I is power over area. The area is 4 pi r squared. Since power is a constant in this case, the source itself is a constant power. 4 pi is a constant. All right, so then, okay, power is a constant, 4 pi is a constant. I is proportional to 1 over r squared. Bingo, simple. Now, we also learned that I is proportional to the square of the amplitude. And therefore, it's also, I is proportional to 1 over r squared, so those two are proportional. Amplitude squared is proportional to 1 over r squared. Put a big root sign over this whole thing. Do that again. A root sign. Whoop! And the a squared goes to a. The 1 over r squared goes to 1 over r. So the amplitude, when you double the radius, just gets cut in half. Not in fourths. But remember, the amplitude, the energy is proportional to the amplitude squared. So when the amplitude changes a little bit, it changes the power and therefore the intensity a lot because of the square factor. If the distance of a sound wave from a source triples, then what happens to the intensity and the amplitude? Okay, well, I2 would be, if you triple it, put a 3 here, 3 squared is 9, so we have what it was divided by 9, 1/9 the original. The amplitude, on the other hand, is just divided by 3. So it's equal to 1/3 the amplitude. There, probably enough about intensity. But the next thing that leads us to, I was saying that, intensity is kind of a real-world reality in terms of what we experience, and that's true. And in the next lesson, I want to follow up that lead a little bit. Intensity has to do with how loud we perceive the sound that we hear. So loudness is something we're going to spend some time with and clarify what we mean by loudness. I'll just say at the outset, it is the perception of the intensity of the sound wave. So you won't want to miss the next lesson.